good afternoon, everyone. How have you been enjoying I/O? Yeah, it makes me sad it's almost over. So we have a few more sessions, and then we all go home. Those of us in developer relations are going to have a party tonight, so it's going to be awesome. I'm looking forward to that. My name is Doug Stevenson. I'm a developer advocate on the Firebase team. I've been working very closely with the Cloud Functions team on getting that product up and running. We launched that back in March at Cloud Next, and I have a few things to say about that. But first, I wonder if you've ever thought about how to build a transactional, multiplayer, real-time game trading system. So just imagine how you might build that in a standard three-tier architecture. So you obviously have some sort of a client app that users are using to perform the trade. And then they're going to need to be connected by some socket to some middleware server. And that middleware server is going to have to negotiate those connections, maintain the state of the trade, generally keep things in sync. In this system, since it's real time, we can expect that there are changing conditions. And so the client kind of needs to stay up to date. And of course, if there's a game, there's going to need to be some persistence, some place to store the state of the game. So traditionally, that would be like a SQL database or something. But it would have to have some sort of a trigger system, because if things are happening in the state of the game that's reflected in the database, those changes have to get proxied back up into the client so the client can be aware of the changing conditions. So in this game trade, maybe the users are kind of figuring out which items they want to trade, or maybe the prices of items are changing dynamically. So there needs to be something there needs to be a way to flow that information back and forth. Now, it's also important to notice that this needs to be transactionally safe. You can't just, float data all around the place and expect that the transaction at the end of the day will happen as you expect. There needs to be some way to account for data contention going on. So think about this system. How many lines of code do you think this would be to implement this? Probably a lot. You'll probably also have to worry about things like provisioning servers. So where does this middleware come from? Where does the SQL database come from? How do you scale it? Now, if you scale it, you have a whole different set of problems. It seems like a lot of work. This is actually designing something like this is well outside the scope of an I/O talk. So I'd like to sort of dumb this down to a simple game of tic-tac-toe. You can think of tic-tac-toe as kind of a multi-user, transactional, state-based system. When you come right down to it, that's what it is. There are rules for engagement. The rules are pretty easy. You probably learned how to play this as a child. I did. It's easy to intuit the rules. Everyone knows how to play a game of tic-tac-toe. But I don't think it's very trivial to implement if you wanted to do something multiplayer on the internet. So just to go over how the game works, in case you haven't played, you have to decide at every turn, is it even the player's turn? You can't play out of turn. Is the move that they're making within bounds? Like obviously, you can't go outside this 3x3 grid. Is it an open space? You can't move other players' pieces out of the way. And how do you determine if the game is over? Well, obviously, you stop when there's 3 in a row, horizontally, vertically, or on a diagonal. But the game has to decide this, right? If you're playing in person, you can kind of informally agree on when the game ends. But if you're directing this through an online game, it's going to have to make the decision. So I would actually like to play a game. I actually wrote a tic-tac-toe game using entirely Firebase. And if we could switch to the demo. Now, there's going to be a URL. Oh, yeah, there's the reminders. All right, so if you load that up, I'm going to try to play, and I'm going to get matched with some of you in the audience. Maybe you're on the live stream. Who knows? I'm waiting for an opponent. Someone type that URL in. By the way, you shouldn't play this game if you don't want your name up on the screen and forever recorded on YouTube. Oh, hey, Stephanie Vasco. Hello, are you in the room today? Oh, hi, Stephanie. Nice to meet you. All right, it looks like it's my turn, so I'm going to make a move. I'll warn you, I cannot be beat in tic-tac-toe. Uh-oh. Stephanie's making a move. I got to block. Oh, thanks for playing, Stephanie. Come and see me at the tent. I'll give you a prize afterwards. All right, so to replay, you can refresh the browser, and I'll play again. Avanti Patil, are you in the room? Avanti. Oh, hi. Nice to meet you. Also in the same row. All right, so you're first, Avanti. All right, so I'll move up here. Now notice that I'm actually trying to move, and the game it's rejecting my moves. Now, a little bit about this kind. So good job, Avanti. See me in the tent afterwards in the Firebase kiosk. I'll give you a prize as well. All right, so can we switch back to the slides, please? All right. So like I said, this was implemented entirely in Firebase. The client is actually quite dumb. It actually doesn't know how to play. It's just giving me the mechanism to make moves, and everything is being decided on the server. So what I did is I used Firebase hosting. So all the CSS, HTML, JavaScript, all of that is being served up by Firebase hosting. It's an edge-cached CDN, so when I deploy it, no matter where you are in the world, you're going to get good performance. I used Firebase Authentication to get logged in. So for those of you who played, you noticed you went through a login screen, and that's how I was able to get your name and your profile picture. So it's just a few lines of code to get that in there. I'm also using Firebase Realtime Database to store the state of the game. So all of the moves that you see, all the records of all the games, is all being stored in a Realtime Database. Now, if you're not familiar with Realtime Database, it's basically a NoSQL database. It's hierarchical key-value pairs, and it's real-time in that you actually listen to the database for changes. So if you're interested in something, you figure out its path, you register a listener, and that listener will trigger whenever data changes. So that's fairly unique. So keep that in mind. That's how real-time database works. And on top of that, there are database security rules that let you determine how users can read and write the database, if they can read and write it at all. Now, there's one other feature I used. I'm not going to say what it is. It's not a secret which one it is. But I would like to at least examine what does it look like to build tic-tac-toe with only those 4 components, with only those 4. And I think it could be done. And the secret sauce there is in the database security rules. So if you're a Firebase user, you probably already know something about security rules. If you don't, I'll just give you a quick primer. So rules are specified in a JSON file. So you have what this is saying is the rules, and then at the root level of the database, there's a location called users, and then there's a wildcard under that called user. And I'm giving that a $sign to say I want to use that value later in determining the rules. So I can say that everyone in the database, regardless if they're authenticated or not, can read this location. However, I can also say that only users who have been authenticated can write here, and their user ID must match the user ID of the location immediately under users. So what we've done here is create a space that's writable only by one user and that user only. And you can also do validation rules. So I can say that any value written here has to be a string, and its length has to be 100. So the write will get rejected if any of these rules don't match. And you can do one other thing. You can write rules that indicate something should be checked in another location of the database versus some information you already have. So what this rule is saying is users can write to the chat location of the database, but only if their user ID is listed under another location called joined. So if your user ID appears under joined, you'll be able to write this location of the database. So between all of these kinds of rules, it's actually kind of powerful. You can express some pretty, profoundly complex rules that dictate how users can read and write your database. So if you do this, if you write fairly complicated rules, what you end up with is a bunch of security rules that determine how users can read and write the database, and you end up with client code that actually does the reading and the writing. And they kind of have to stay in sync. You can't change your security rules without changing your client code. And if you change your client code, you need to change your security rules. So it's powerful, but it's kind of inconvenient. That's the fact of the matter. When your security rules get very complex, it becomes inconvenient. It's also not cross-platform, because you still have all this logic in the client that needs to be duplicated for Android, iOS, and the web if you're supporting all those platforms. And it's also kind of difficult. When the rules get complicated, they get long, and they're difficult to test, and they're difficult to debug, and they're, quite frankly, difficult to read as well. And it turns out there's this open source project called Firesafe. And Firesafe was written by one of the Firebase engineers before he became a Firebase engineer. It tries to smooth out some of these things. So with Firesafe, you can express the rules for engagement in a multi-user transactional system, and specifically transactional system, and it will actually generate the security rules for you. This is kind of what they look like. Now, I think you would agree, this is kind of hard to read, right? It's kind of it requires a lot of brain power. My brain's melting just looking at it. I'm not even going to bother trying to unpack it. This is actually the second stage in a 10-stage step of doing an in-game trade. So you imagine this times 10. This is what your security rules look like. Basically, you're saying there's a role for the person doing the trade. What state are they coming from? What state are they going to? What is the signal they're sending to the next state? And all the rules that determine how you can progress from one state to another. This is a lot. If I was writing a transactional system, I would probably not opt to do it this way. But if you ended up doing it this way, you would end up, at the end of the day, with a state machine that determines how clients interact with the server and interact with each other, essentially through the server. So they're using the server as a middleman to kind of negotiate these connections. Now, there's another problem here is if you implement your transaction this way, if one of the clients sort of disappears at some point, the transaction's basically dead. You kind of don't have a way to recover. So if something goes wrong, the whole thing is messed up. And what you probably want instead is a single source of truth for all of your logic. You don't want to split it between the clients and security roles. You'd rather have it all in one place. So I use Cloud Functions for Firebase to implement this. All of the game logic in that tic-tac-toe game is coded up in Cloud Functions. The client actually, like I said, does not know how to play tic-tac-toe. It just lets you move as much as you want, anytime you want. Everything is being controlled at the server. Now, Cloud Functions is part of the Google Cloud Platform. But for Firebase, we have additions onto that. So for Firebase, the product is called Cloud Functions for Firebase. You can do things like write database triggers. So if something changes in the location of your database, you can trigger some function and have it do some work. You can trigger on authentication events. So when a new user signs in, you can know about that and do something. Or if a file is uploaded to your storage bucket, you can do something about that. You can also write HTTP triggers. So you can write basic webhooks as well. But the best thing about it is it scales up and down. So when you first deploy your code, and you only ever deploy code, you don't manage servers at all. When you deploy your code, it goes to Google servers, it gets published, and it sits there waiting for something to happen. So if nothing happens, you don't pay for anything. There's no action. The moment users start to use it, it will scale up, and it will scale up as much as needed to support your app. And it will also scale down. So if your users drop off, you can scale down to 0, and again, you're paying nothing if you don't have any activity. So what I did here is I implemented, with Cloud Functions for Firebase, the state machine that represents a tic-tac-toe game. The way that clients interact with this game is they express intent. They don't write to the database directly. The clients just say, I want to play, or now I want to move here, or I want to, I want to check in. And I'll talk about all this later. But like I said, Cloud Functions decides, based on that intent, what to actually do. The clients aren't actually doing anything other than expressing intent. So what I have is a command structure. The way I ended up doing this is I used Realtime Database as a proxy. So you write into the database to say what you want to do. Then the game state is updated based on that intent. So sending a command basically looks like this. It's a little pseudocode. So what the client does is it grabs the user ID from the currently authenticated user. It builds a path to a location of the database that it wants to write to. So here, the path is /command/ whatever your user ID is. And we create a reference to that. With that reference, we can then push data into that location. And a push is essentially saying, I want to write an object, and I don't know, I know where I want to write it, but it needs to have some unique ID. So push will create some sort of unique push ID, which is a random time-based identifier. And you can find out what that is on the client. So for my commands, a command object has a property called command. It has the name of the command in there, and then some number of arguments, maybe 0, maybe 2. Now, on the Firebase side, there's security rules that protect how users can write into this commands area. So again, security roles under commands, and then under that, the user ID, and wildcarded user ID, I can say, no one can read here, but only that authenticated user can write here. So this is protected. Only users can issue commands on their own behalf. No one can sneak in because it's protected by security rules. And in the database, what it looks like is this. So there's /command/ whatever the user ID is, / whatever that push ID is, so I'll call it command ID, and then the command object itself. So that's kind of how the client says what it wants to do. And in the function itself, so this is Cloud Functions code. It's written in JavaScript for the Node environment. All you really do is require Firebase functions. This gives you the ability to express what a function can do. So in here, I define a function called command. And the reference is, it looks just like what is being sent on the client side. So under /command/ some wildcarded UID / some wildcarded push ID. If anything happens that matches this pattern, this function is going to trigger. It's going to trigger with an event object that contains information about what the user's trying to do. So I can pull the user ID out of the wildcard. I can pull the command ID out. I can pull the command object itself from that location of the database. And I can find out that command name that says what they want to do. And then I can act on the command name. And then there's hundreds of lines of code missing in there, of course. And then I'll delete the command when I'm done. So the first thing that you saw, for those of you who played the game, is you got matched. So I waited for someone to play. You were all waiting for each other to play. There's a player matching part. So how does this work? Well, the first thing we need to do is get 2 players who have expressed intent to play. And then we'll initialize a game, and that becomes their space to interact and transact this game. So there's a simple command for that. It's just match. There's no arguments. The client sends that up and saying, I want to play. And then what happens in the database, that gets pushed in. So under /command/ UID / command ID, this command is sitting here. Now, when that write happens, Cloud Functions kicks in and says, I can do something now. So the way I implement matching is that there's another location of the database under /matching. And it has two states. There's only two states it can be in. It's either empty, meaning no one's waiting to play, or there's a UID there, which indicates that there's someone waiting to play. And what the code does is it basically flips that toggle. It either accepts a new person into that waiting room, into this lobby, or it matches the existing person with someone else who wants to play. Now, after we've matched two players, we need to create some sort of game space for them to play in. So I've defined a simple object that contains the player 1 user ID, the player 2 user ID, the user ID of whose turn it is, and in this game, player 1 always gets to go first. And then there's a list of moves, and this move sort of accumulates all of the things that both players have done. And then there's an outcome at the end, so that can be either a player 1 win, or a player 2 win, or a tie. And the move is just a simple number of the player, the x coordinate, and the y coordinate of the location. So this is the game state. This holds the state of the game of tic-tac-toe. So what I'll do is I'll push this under yet another location of the database under /games. And because we're pushing it, we'll generate some random game ID. We don't know what that is until the push happens. And then the state object goes under there. Now, we have a little bit of a problem because the clients need to know what's in here in order to play. They need to know so we can render on the screen what the tic-tac-toe board looks like. So the question is, how do we get that game ID of the client so they can listen to it? If they don't know what the game ID is. The push happened on the server, not on the client. So what we need is a way to notify players that something changed. So the way I chose to implement this was to create another location of the database called /player_states. And under there's some user ID that matches the user that's playing. So what happens is the Cloud function will write the game ID into this location, telling the user, hey, you're in a game, here it is. And then what happens is the clients can turn around, use that game ID to construct the path, define the state. So this is what happens when you get matched and you move into the game. The client is saying, oh, I'm in a game, now I need to transition to the game screen, and now I need to render what's in that game state so the player can see what's going on. So now we have to figure out how do the users participate in this game. And it kind of makes sense to let people write their moves into the database, right? That's the first logical thing to want to do. But I don't actually want to do that. I actually want to assume that the clients are malicious, that they're going to send me bad data, that they're going to move invalid, they're going to move out of turn. I don't want to have to trust my clients. I'm just fundamentally distrustful. I don't know. There's something about me. I would rather have that decision being made on the Cloud Functions side. So what I'll do is I'll actually lock down read access to that entire games node. No one can read it. I'm sorry, no one can write it, but everyone can read it. So this makes it so that every game is essentially public. If you know the game ID, now you can observe the game. If you didn't want that, you could go further and try to lock down access to different players. So if you have the player, so with P1 UID and P2 UID, you can tell Realtime Database, only let these players see what's in the database. So you can do that if you wanted. And the security rule for player states is also locked down to just that user's user ID. So when we push data into that location, only the user who can see that, right? It's locked down to that user ID, and no one else can write it. So to actually make the move, now we need to start to implement the rest of the state machine. And I won't go into detail. I think it's kind of obvious. Like I said, players have to take turns. They have to make valid moves. We have to check for a win, and then we'll end the game. So there's a command called move. So when players are in the game, they'll issue a command called move, and there'll be XY coordinates for the location. Now, this is going to get pushed into the database under command /UID /pushID /move, and then the Cloud function is going to trigger and handle this move. And the only way we can do this safely is with a transaction, because we have to assume, because the client's not restricting you, you can move whenever you want. You can do you can try to cheat as much as you want, but this Cloud function, because it's transactional, because it's basically handling the contention for all of those moves, can do this safely. So we'll construct a 2D representation of the list, or of the move list. We'll check the validity of the move. We'll simulate the move in memory, check for a win, and then update the game based on that. So if someone tries to make an invalid move, we'll stop and not even update the game. It'll just fail, and then we can actually send a message back to the player saying, you can't move there. So we do want to notify the players after the move of the state change that happened. Now, you might be wondering, if clients are listening to that game data, if they can see the game, well, certainly they saw that there was a move, but I want to personalize it a little bit. I don't want the player to have to guess if it's their move, and I don't want them to have to guess why their move was rejected if they moved out of order. So what I want to do is use that player states area over again and say, we have the game ID, that's great, but I also want to send a message to the user and say, it's your turn now, or we're waiting for the other player, or you made an invalid move, or the game is over, you can't move anymore. So we can put messages in here. And again, it's the server server that's deciding these messages. It's not the client. The client, again, doesn't know how to play. The server knows how to play, and it's telling the client how to play. Now, there's a more generalized pattern here. So in my system, things come in through commands and out through game and the player states. But you can think of this much more generically. So imagine a system where you have a command and response cycle. So say you push commands into the database, and Cloud Functions picks it up, and then it writes a response back. Now, when you push that command in, you get a push ID. The client knows what the push ID is because it pushed it in there. Then it can turn around and listen to a known area for that response. So notice the command ID is the same. You could do this to implement kind of a transactional system. And you might be looking at this thing, well, this just looks like an HTTP transaction, right? Why don't I just do HTTP request response? That's a good question. You could implement this way, but I think there's a certain benefit to using real-time database and Cloud Functions as sort of the middleman here. So this is actually resilient to connection problems. So I don't know if you've ever encountered this problem. If you have an app that's making HTTP transactions, it wants to do a write operation, but the connection gets cut off. Do we know if that write finished? Well, we don't. We didn't get a response. So do we retry that? Or is it safe to retry that? Or can the server detect if it's a retry? And we don't really know. That connection's lost. The context is gone. But if you're using real-time database as a middleman here, you're pushing that command in the database, and then real-time database just synchronizes. And it synchronizes once and only once. You don't have to worry about a retry. So when you push that command in there, you can be fairly certain if the user has a data connection that it will hit a Cloud Function once and exactly once. And so there's a benefit to that. There's also authentication built in here. So if you use the user ID as sort of a way of filtering who can write at what locations, you actually have authentication built in for free. So you don't have to do that over like an HTTP connection that you would normally. And this is also helpful for Android apps. So I'm an Android developer. I don't know if you all are Android developers or web developers or iOS developers, but Android apps actually have a very particular problem where if you have an orientation change, activities get destroyed and they come back. And now you've lost your context, right? You have to figure out how to reconstruct the state of the new activity based on the old one. Again, this is a problem particular to Android apps. But this losing of context has to be dealt with. You can't not think about it. So you end up using something like a loader or a headless fragment, or have some other scheme of trying to figure out how to keep the thing that was going on in the one activity going again in the second activity. And those are kind of problems, and I just don't like to think about those problems. If you're using real-time database as sort of a middleman for pushing commands to Cloud Functions, all you really need to do is remember that command ID. Once you push a command in there, just remember that string, persist that into your new activity. You can pick up where you left off, just listen for the response, and expect that it'll happen. So I think that's kind of neat. Now, that's basically how the game works. And there's a problem in this game with ghosted players. So imagine you're in a game, you know you can't win. What do? If you don't want to chalk up a loss, you might just close the browser window or kill the app. And that's kind of unfair. The person who's winning should get that win, right? So how do you deal with this? How do you know when someone pulls out unfairly? So there's a couple things you could do here. You could do like a scheduled ping. So if you're thinking, like, maybe I could ping the game every once in a while and check to see if someone's gone or they haven't moved in a while, you could do that. It turns out Cloud Functions doesn't really have a way to schedule like cron jobs or at jobs. It would be really nice. I think that the team is working on that, but we can't do that today. If you're using real-time database, you might also be tempted to use on-disconnect handlers. So with real-time database, you can schedule, or you can arrange for a certain location of the database to change if a client connection goes away. You could use that to determine if they're gone. But I don't really like that either. I think mobile connections are generally kind of flaky. So I don't know if you know, but if you're on Wi-Fi and then you switch to mobile, or you're switching between towers, you're in the basement and you don't have a good connection for a while, I don't want that disconnect to sacrifice the game. I would rather let the user drive through the tunnel, come out on the other side, and still be able to keep playing. If you use an on-disconnect handler, you still have that problem. So I would rather not do that. Oop, I went too far. So instead, what I did is I implemented a periodic client check-in. So the idea is the game, the client doesn't know how to play the game, but it knows how to say, I'm still alive. So periodically, it'll run a function called check-in that will basically ping the game and say, I'm still playing, I'm still here, I'm not gone yet. And what happens is, again, we'll create a transaction on that game that the user is playing. And what happens is, the player one check-in basically looks at player two and says, if they haven't checked in a while, I'm going to make them forfeit the game. And it's the same way for player two going to player one. Player two, their check-ins will essentially force player one out if they've been idle for a long time. So this is kind of a way to work around the inability to schedule something or the inability to just run something at an arbitrary time. Now, this game, I would like to open source. I haven't open sourced it yet. I kind of scrambled to get this done at the last minute. So if you want to follow me on Twitter, I'm Coding Doug, and I'll post that there. Also, for those of you at home watching on YouTube, I'll try to get that link embedded in the description below. So be sure to stay tuned if you want to see how it works. The project is relatively small, I would say. It's about 200 lines of JavaScript on the client, and I'm not using any frameworks. It's just straight JavaScript. On the Cloud Function side, it's about 700 lines of code, which is not that much. I mean, a lot of that is scaffolding and doing the transactions. It's actually not that complicated. And you'll see that the client is so dead simple, and it's great because you don't have to depend on the client being compromised. I just kind of assume that people will hack clients. I assume that people will hack games. And you can see in this game, I'm not even trying to prevent anyone from hacking anything. Everything is controlled on the server. OK, so how might we improve this? So this is a pretty simple game. It was put together in basically a handful of days. How might we improve this? So one thing we could do is implement a leaderboard with a web API. So we might have, you might be able to remember what users are doing in your app. You could create an HTTP cloud function that can access that leaderboard data, and you can populate that in your website. So that might be kind of neat. You could also create an in-game chat. Firebase apps are very well known for being chat apps a lot of times. Everyone wants to know how to use Firebase to put chat in your app. And Firebase did come from roots as a chat system. So you could implement this as well. You could also post game results to a Slack via a webhook. So say you're in a tournament system and there's a very high-profile game going on, and there's a lot of people in a Slack sort of chatting about it. You could use the Slack API to post via their webhook and notify everyone that a game is complete and what the outcome was. You could also use Cloud Functions to create some sort of resistance to bots. So like I said, I kind of assume people are going to cheat all the time. And that includes creating bots that will try to play the game very effectively, maybe more effectively than a human. You probably want to stop that if you're playing for money or playing for points or playing for prestige. So you probably want to validate that the user is a real user. Google has some APIs. There's something called reCAPTCHA. You click that little box to prove that you're human. You could wire that up into Cloud Functions and make sure that no one can play until they've satisfied their reCAPTCHA that validates their humanity, basically. And that's all I have for today. If you have any questions about Cloud Functions or Firebase or anything, I'm going to be in the tent next door. If you have any comments or concerns about, is Cloud Functions right for you or is Firebase right for you app, let me know. We have a bunch of people over there, Firebase staffers, myself, would love to talk to you about how Firebase can work for you. And don't forget, we have documentation. We have a YouTube channel with a lot of tutorials. We have a blog. I contribute to all those. Let me know the kind of stuff that you're interested in. I could make material for that. And thank you very much. I hope you enjoy the rest of your day.